What's up guys, and welcome to this video. We are going over the 2018 physics exam. This is the DBE exam. Okay, so Department of Basic Education's exam. Okay, so we're going to start off with question 9. Okay, and the reason for that is because I have been requested to make some more electric videos, or electric circuit videos, so I decided to start here. Okay, so this is on electric circuits. Okay, so let's get straight into the question. In the circuit diagram below, the battery has an unknown EMF there and an internal resistance of 0.8 ohms. So question 1, okay, so let's just look at this diagram quickly. We have a parallel branch, a ammeter, 5.8 ohms there, 0.6 amps there, the internal resistance of 0.8. Yeah, okay, so question 9.1.1 says state Ohm's law. Okay, so Ohm's law says that the potential difference across a conductor is directly proportional to the current in the conductor at a constant temperature. Okay, so constant temperature. Okay, so basically the equation we get out of that is V is equal to IR. This is the governing equation for Ohm's law. And we get ourselves 2 marks. Okay, so the ammeter reading A2, this one right here, is 0.8 amps when the switch is closed, as it's shown in this diagram. Calculate the reading. Okay, so question 9.1.2 says calculate the reading of V1. Okay, so V1 is this voltage across that branch right there. Okay, so using the equation V equals IR, we know what the current is. Okay, so we know the so we're looking for the voltage, right? V1. So V1, we know that the current is 0.6 amps in that branch, and we know the resistance is 4 ohms. Okay, so the answer comes out at 2.4 volts. So V1 has a reading of 2.4 volts, and we also know that that is the exact same reading as the branch there. Let's say that's V1 as well. Okay, and that leads on, and we get 3 marks for that. Question 9.1.3 leads on, says calculate the current through the resistor, the 6 ohm resistor. So we can say that V equals IR once again. The voltage now is so the voltage across the 6 ohm resistor is that same voltage. So 2.4 is equal to the current, which is the unknown, times our resistance, which is 6 ohms. Okay, and if we solve for the current, we get a value of 0.4 units of amps. Okay, so let's actually put that in there. So the current here, A equals 0.4. Okay, and we get ourselves 2 marks for that. Okay, the reading on the voltmeter V2. Okay, so we want to know V2. Okay, so how are we going to do this? Okay, so again, we can just say that V2, using Ohm's law, so 9.1.4, V2 equals I times R, right? But we also know if we look at this branch right here, let's look at this node right here, right? So we have I1, let's say that's I1, we have I2 going out, and I3. Okay, the current is splitting according to Kirchhoff's current law. So I1 is equal to I2 plus I3. Okay, and we know what I2 and I3 are. It's 0.4 amps, and the current through that is 0.6 amps. So in total, so what we have is 0.4 plus 0.6 is equal to 1 amp, right? Is the current going through here. So the current A1 is equal to 1 amp. Okay, so we can say is equal to I, which is 1 amp, times our resistance, which is 5,8 ohms. So V2 is equal to 5,8 units of volts. Okay, another way you could have done this instead of showing this, I mean, you'd have to show this calculation right here. Otherwise, you could have said it is 0.4 plus 0.6 times 5,8. Okay, gives you exactly the same answers. Here we just split up calculating our current. Okay, and finally, we want to calculate the EMF of the cell. So let me just give myself some space. Okay, so question 9.1.5, we can say that if we go to our formula sheet, let's see, if we go to our formula sheet, electric circuits, we can use this equation right here. The EMF equals our I times our R plus our internal R. Okay, so R external plus R internal. So let's go there. EMF equals our I times R internal or R external plus small r. Okay, so now the question is, what is our external resistance? Okay, so I'm going to clean up this whole thing. Okay, so we have to calculate our external resistance. Okay, so the easiest way to do this would be to first calculate the resistance of this branch, R parallel. Okay, and then we can simplify this into a circuit that looks something like this. We have R parallel, we have a 5,8 ohm resistor, and we have our cell with a 0,8 ohm resistor. Okay, so we need to calculate R parallel first. So we know the equation 1 over R parallel is equal to 1 over our branches, so it's 1 over 6 plus 1 over 4. Okay, so if we solve for R parallel is equal to 2,4 ohms. Okay, so now what is our R external? R external is going to be equal to our R parallel, okay, plus in series of 5,8 ohms. And then our R internal is 0,8. Okay, so we can solve for the EMF now. So the EMF is equal to our I through the circuit, through the external circuit, which was 1 ohm, times R parallel, which was 2,4, plus our 5,8, which gives us our total R external, plus our small r, which was 0,8. Okay, and if we solve this, we get that the EMF is equal to 9 volts. Okay, and that's our final solution. Okay, so, and we get ourselves 3 marks for that. 9.1.6, calculate the energy dissipated as heat inside the battery if the flow, if the current flow in the circuit is for 15 seconds. Okay, so there's a number of ways we can go about this, but we're mostly worried about the battery. So we can say that the heat generated or the work is equal to our I squared R in the battery, which is our small r, times our delta T. Okay, so I squared is 1 squared times our R, which is 0,8, times our T, which is 15 seconds, and we get that the heat dissipated is equal to 12 joules. Okay, so there are a number of ways you can go about it. You can try using the equation W equals our voltage times our current times our delta T. Okay, and that would be, remember all of that is for to calculate the work, or we can even use the equation. It's equal to our voltage squared over delta T times delta T over the resistance. Okay, remember we're using small r here, because we want the current flow inside the battery, so the heat dissipated inside the battery. But for me, this is the easiest way to get to the answer. It's just our I squared R times T, noting that R is our small r. Okay, and that's the end of that part of the question. Then we move on. So question 9.2 says a simplified circuit diagram for a windscreen wiper of the car consists of a variable resistor and a wiper motor connected to a 12-volt battery. So we can see the schematic. So we've got our variable resistor, 12-volt battery, our switch of some sort, and our wiper motor. Okay, so when the switch is closed, the potential difference across the variable resistor, so when it is closed, the potential difference across the variable resistor is 2,8 volts, and the current passing through it, so the current I is equal to 0,7 amps. Okay. Okay, so question 9.2.1 says calculate the resistance of the variable resistor. Okay, so we know the current and the voltage across it, so we can say that V is equal to IR. We know V is 2,8, we know I is 0,7, so we have to just solve for R, and if we solve for R is equal to 4 units of ohms. We get 2 marks for that. Question 9.2.2, the resistance of the variable resistor is now decreased. State whether the speed at which the wiper turns increases, decreases, or stay the same. Okay, and we have to give a reason. Okay, so let's work through this just by using the equation V equals IR. Okay, so V is equal to a constant, right? And we know that it's equal to 12 volts. Okay, so if V is constant and R decreases, so R goes down, so therefore to make V a constant, I would have to do the opposite thing. It'll have to go up, right? So therefore the current goes up, so the current through the wiper motor would increase, and therefore our power would also increase, so the motor would turn faster. So to answer the question, question 9.2.2, state whether the wiper turns will increase. So yes, it will increase. Okay, and the reason for this is we can say that the total resistance has decreased, therefore the current and the power, and therefore the power has increased, and so the motor turns faster. Okay, and that's the end of that question, and we get 3 marks. So we've gone through this entire question, so we would have got our full 20 marks for that. So not too bad of a question, quite interesting, a little bit of thinking there towards the end, but other than that, yeah. Thanks for watching, guys, and I hope you found this useful.